Okay, so this is going to be like the last lecture on, what is it, chapter 6 or something, on independent sets. Um, so the question we're going to focus on is what is the maximum number of independent sets in a D-regular graph. D-regular, I don't know if we've mentioned this, what this means, but it just means all vertices have degree D. So D is some number. So we want to maximize independent sets in a D-regular graph on n vertices. So you've got two parameters here, like D and N, and then we want to like maximize the number of independent sets given these two parameters, right? We're not going to actually solve this problem, but even though this is a solved problem, but we're going to give sort of a rough bound. So maybe first, as an example, let's look at like the graph KDD, complete bipartite graph. How many independent sets does it have? It's like not a super hard problem, but it's really easy to get this wrong by like a little bit. But can anyone, hey, let's try to work it out. Any guesses? Or so, because you're taking basically a subset of this side or a subset of that side, right? There is also one other one, which is the empty set. So yeah, this is one way to kind of compute it. Which, when I sum, well, okay, so both ways are going to give me the same answer. Like, or, I mean, in fact, I'm sort of doing the same thing. So another way to think of this is I could take a subset of the left side or a subset of the right side. So it's like kind of like 2 times 2 to the D, because there's 2 to the D subsets of this side, 2 to the D of that side. But then I counted the empty set twice, because the empty set's a subset of both sides. So it's like this minus 1. And if you like, if you compute this, you get the same thing. So it's 2 to the D plus 1 minus 1. Right. Now, okay, this is a very specific graph on 2 times D vertices. But if I take, let's say suppose n is divisible by 2D. If I take, so one example could be, if I take disjoint copies of this. So let's, imagine you take n over 2D of them, where we assume n is divisible by 2D. Then you'll get the number of independent sets is just, to pick an independent set of this graph, you just take an independent set in every component. So it'd be 2 to the D plus 1 minus 1 to the n over 2d in this graph, right? Okay, so there is a theorem that we're not going to prove, but this is a known theorem. But actually, this construction is the best possible thing you can do. So for any graph, for any d-regular graph on n vertices, the number of independent sets in G, so graph G on n vertices, is at most 2 to the d plus 1 minus 1 to the n over 2d. So this is kind of a combination of two papers, one by Jeff Kahn and one by Yufei Zhao. So it implies this result. But like I said, we're not going to prove this. So actually, the purpose of this lecture is, well, in mathematics in general, there are two sorts of approaches to a given problem. I mean, you could have suppose you're trying to solve something, sometimes if you want to get a completely, perfect optimal result like this one, it might require a sort of tailored approach to that problem. But another kind of often we can also come up with techniques that are, applicable, maybe not to get the optimal bound in certain problems, but you can apply it to a wide range of problems. So the technique I'm going to talk about today is kind of the second type, where basically I want to get a reasonably good bound on the number of independent sets in a graph, in a regular graph. It's not going to be as good as this, but the approach that we're going to use can be applied to a lot more problems. So what we're going to prove so this is a theorem that we will prove. So this is an older result of Noga Alon that says that for all epsilon greater than 0, there exists some d naught of epsilon such that if d is at least this d naught, so if d is big enough, then every d-regular graph on n vertices, and I don't really care what n is, it just has to be big enough for this graph to exist, I guess. So every d-regular graph on n vertices satisfies that the number of independent sets in G is at most 2 to the power 1/2 plus epsilon times n. I should probably maybe relate these two theorems. So this, I claim, this theorem is weaker than the previous one, but it's sort of close to, it's sort of close to being as good as this one in some sense, right? Because, okay, this is to the d plus 1 minus 1 to this power. If you think of I don't know, n as being large or something, this minus 1 isn't making a big difference, right? So you can kind of think of this thing as being like kind of 2 to the d plus 1 to this power. So, or if d is large and n is large, and you can kind of think of this as maybe something like 2 to the d plus 1, So I'm being a little bit wishy-washy here, but let's just kind of think of this minus 1 as not really mattering too much. And then this would be like 2 to the, 1/2 plus 1 over 2d times n. And that 1 over 2d, you can think of like an epsilon, whereas d gets bigger, this gets, smaller, right? So it pretty much is like 2 to the 1/2 times n, kind of, with this little error term that goes to 0 as d goes to infinity. And that's exactly what we've got here, is like a 1/2 plus some epsilon. And if d gets bigger, I can make the epsilon smaller, because eventually d gets bigger than this d naught of epsilon, and that means I can make epsilon smaller and smaller and smaller, right? Okay, any questions about that? So we're going to prove this kind of weak version of this result. And like I said, the purpose of this is actually just to show you a cool kind of method that's, like as we're going to see, the approach we're going to take to proving this, it's not, I mean, in some sense, it's going to use a little bit of, the hypotheses here, but like in a very weak way. And so it's nice because it's applicable to many different problems. So this is something called the container method. Okay. Okay, before proving this, actually, I think I need a lemma. So if we're trying to prove this, one thing that could kind of ruin it for us is, like, if this graph G has suppose it has an independent set with like, if it has even one independent set with more than like 1/2 plus epsilon n vertices in that independent set, then any subset of that independent set is an independent set, and that would kill, we would not be able to prove this upper bound, right? So one thing we need to know is, okay, if you have a set that is bigger than half the vertices, it can't be independent. And moreover, it's useful to have a quantitative version of that saying, if it's much bigger than half the vertices, then it's far from being independent. So let's say, again, G is D regular, and vertices. The statement the statement we're going to want is if S is a subset of the vertices such that the size of S is at least n over 2 plus t, where t is some, think of t as some non-negative number, but even if it's negative, it'll be fine. It'll just be trivial. So then the number of edges within S, which I'll write E of S, is at least t times d. So basically what this is saying is if I've got a set that's significantly bigger than half the vertices, well, first of all, it can't be independent. And second of all, like in fact, it's got to contain kind of a lot of edges in some sense. But this is kind of easy. Like maybe I won't prove this, but like it's kind of handshaking, right? Imagine I've got a set S here of more than half the vertices. So this is like V of G minus S. Every vertex has degree D. So like the total, if I look at how many edges are sent from here to here, like how many edges go from this set to that set, each of these vertices only contributes at most D edges this way. But then if you think about it, everyone here has to have degree at least D, and there's more of these vertices than there are these ones, right? So in order for these ones to all have degree D, basically they've got to be, these ones are only sending D each, right? So there's got to be kind of a lot of edges among these ones to get their degrees up to D, basically. So that's the whole proof, and then you just count it carefully and you get this. Okay, any questions about that? So yeah, number of edges, I guess, from S to V of G minus S is at most V of G minus S times D, and then like kind of use this and the fact that all of these vertices have degree D to get a lower bound on this. Okay, so let's prove the theorem. Maybe a bit of notation. Let's let curly I of G be the set of independent sets in G. Okay, and what we're trying to do is get an upper bound on the cardinality of this collection. So yeah, we want it to be at most that big, where like at some point we're going to have to say, okay, D is large enough such that something, and yeah. Okay. Okay. So let's pick a few parameters, but maybe we'll talk about them kind of later. So I'll just say let M be large with respect to epsilon. And what I mean by that is like the smaller epsilon is, the larger M is. So as epsilon gets smaller, you make M larger. And we're going to let D be large with respect to M and epsilon. But of course, since M just depends on epsilon, if D depends on M and epsilon, then it just really depends on epsilon, right? So yeah, so basically the smaller epsilon gets, the larger M gets, and the larger D gets. Okay. Okay, so what we're going to do is run an algorithm on our independent sets. Maybe I'll write this over here. So another thing we're going to do from the beginning is just fix an arbitrary order V1 up to Vn of the vertices of G. this might not seem important, and it's like, I mean, isn't super important in some sense, but basically what this ordering is going to do is we're going to run an algorithm, and we're going to like try to say, we're going to often say like, pick the vertex that maximizes some parameter. But there might be a tie, right? And basically this ordering is going to be used to like break ties. And the thing is, if I run the algorithm once on one independent set and once on another, if I have the same situation, like if I'm in the same scenario, I've got the same tie that's happening, I want to break the tie in the same way every time. But if I just say, okay, break the tie by picking the one earliest in the order, that's going to break the tie in a consistent way. So this is like fixed before we even define any algorithm. And it's totally arbitrary, doesn't matter. Okay, so for each independent set, we construct two sets, Fs, so S is the independent set, and Cs according to the following algorithm, so as follows. Okay, and just to explain the terminology or the notation here, F is going to stand for fingerprint. So this isn't going to mean anything to you yet, but maybe it will later. So we think of that as the fingerprint of S. It kind of identifies S in some sense. It's basically like a small amount of data that kind of corresponds to S. Well, okay, no, sorry. Many different independent sets may have the same fingerprint, but anyway, for whatever reason, we call it a fingerprint. And C of S is going to be called the container of S. Okay. Essentially, what we want to do is associate every independent set with a small fingerprint and a not too large container. We'll see what that means in a minute. So here's the algorithm. Let's start by initializing Fs to be the empty set and Cs to be V of G. Okay. Okay, and now we're going to start processing the independent set in some sense. So as long as there exists a vertex, let's say V, in the container, so in the current, like, we start with the container being everything and we keep processing it, so it's going to change in every step. So this is kind of the current container. So while there's something in there such that it has at least m neighbors in the container, where m is this like mysterious parameter we picked at the beginning, and we'll talk about it more later, how big it has to be. Okay. So, okay, as long as this thing exists, we're going to pick such a vertex to maximize this quantity. Of course, there might be a tie. Two vertices may have the same number of neighbors in this thing, and if so, we pick the earlier one in the ordering. So let like vi be such a such a vertex where we actually maximize this number of neighbors, and subject to this, I is minimum. Okay. So just pick the earliest one in the ordering. Okay. So now we get into two cases. Or let me say, I don't know, case A or something. Oh, yeah?
Sorry, it says let VI be such a vertex where the size of the neighborhood of VI intersect CS.
Oh, is maximum. Or, in fact, I don't even think I need this. Let's just say such a vertex where I is minimum. Yeah. But what I meant to write there is to make this thing as big as possible, but that's not even going to matter, really. So let's just say where I is minimum. Simpler. Okay. Well, so now we're going to look at VI and say, is it in the independent set or is it not? So if it's not in S, that's the simpler case. We update CS as follows. So this is kind of like, I don't know, notation for like pseudocode or something, right? I mean, or maybe it isn't. I don't know if I'm using this right or not. But what I'm trying to say is take this thing CS and change it to CS minus VI. So VI used to be, like, because we were taking a vertex in the container. It used to be in the container, so now we just take it out. And don't change the fingerprint. So FS stays the same. Case B, VI is in S, and then we update CS to, so we remove VI, like we did before, and we also remove all of its neighbors. Well, all the neighbors that were in CS, but. And then we update FS. So we put VI into FS. So it goes into the fingerprint. Okay. And then we just keep repeating this. So this is like a while loop, right? So then we process it, VI. We go back here and we say, is there still a vertex with this property? If there is, pick the minimum one. Look at if it's in S or not, and process it as follows. Go back and keep doing this. Okay. So in particular, like initially, right, CS was everything. Like the container was the whole vertex set. So in the first step, what you're going to do is you're going to say, is there a vertex of, degree at least M? I mean, if M is at most D, then there is. And you just pick the one with minimum index, which would be V1. You just look, then you process it in this way, and then you go back and keep doing this. Any questions about the algorithm? Except for like, why would we do this, and why is it relevant? Okay. Okay, let's make some observations. So when this terminates, like, every vertex in CS has less than m neighbors in CS, right? Otherwise, we would have continued. So the total number of edges within the container is going to be less than m times CS over 2 by, so this is just handshaking. The over 2 is because like when you sum the degrees, you count the edges twice. So yeah. Which, of course, this CS thing is like less than n over, it's less than n, or less than or equal to n. So that's at most mn over 2. So by the lemma, the one that I just erased, this container can't be too big because it's we've kind of bounded the number of edges inside of it, so it can't be bigger than n over 2 plus n times m over 2d. Okay. So if you want to check that, think of this number as being t. So in fact, this is strictly less than. Like this number as being t, and then plug that into the lemma, and you would get at least t times d edges. That cancels the d, so you get n m over 2, and that's like the number we have here, right? Okay, so this CS thing is, it could be a little bit bigger. The container could be a little bit bigger than n over 2, but not by that much. Okay. This is kind of going to contribute, like if we pick, if we pick for d large, remember d is large with respect to n and m and epsilon. We can say that this is like less than or equal to, let's say, n over 2 plus epsilon over 3 times n or something, right? So in other words, 1/2 plus epsilon over 3 times n, right? So this is kind of one place where like an extra epsilon is going to come from. Okay. So this tells us that our containers are not too large. And now what I want to say is that our fingerprints are really small. So the observation is, like, think about each time I increase the size of the fingerprint, that can only happen in case B, right? Like when case A happens, the fingerprint doesn't change. In case B, I increase it by 1. But every time I do that, so the fingerprint goes up by 1, but the container size goes down by like m plus 1 because it loses VI and all of the neighbors of it that were in this thing, in the container. So, so each time Fs goes up by 1, CS, so let's say the cardinality goes down by more than m. It's in fact like m plus 1. So since the container started at size n, like, so this thing can only have increased n over m, less than n over m times. So yeah, our fingerprint is less than n over m because each time it goes up by 1, the container goes down by, let's say, m or even more. So it couldn't have gone up more than this many times. Another observation is that the container, or the fingerprint, is a subset of S, and S is a subset of the fingerprint union the container. So part of the reason for the name container is like it kind of contains the set S, although it doesn't quite because you need the fingerprint as well. But this just comes from observing how the algorithm runs, right? Every time you add something to the fingerprint, it's because it was in S. And so this containment holds. And in each step, if there's something in S, like basically in this first case, when I remove something from the container, it wasn't in S anyway, like in case A. Like so the second inclusion, it holds at the beginning, right? Before we've done anything, it holds. And in each step, when I do this, it does not, it will not cause that thing to be violated. And then also, in this case, the things I take out of the container are VI, which I put into the fingerprint. So that's kind of fine. I take out the neighbors of VI, and we know that if VI is in S, then its neighbors are not, because it's an independent set. So also in this case, it does not ruin this condition, right? So there was something in CS in the container that was in S, and we remove it, but we put it into here, and everything else we remove wasn't in S. So. Okay, any questions about this? It's kind of a lot to process. So here's the super key observation, okay? All of this stuff is important, but this is like the thing that makes everything work. So what I want to claim now is that if S and T are two possibly different independent sets, if they have the same fingerprint, so if Fs equals Ft, then they've got the same container. This takes a little bit of thinking. Is it clear what I'm saying? If somehow I run this algorithm on two different independent sets and the output gives me the same fingerprint, then it also gives me the same container. Okay. The reason is that basically, like, knowing the fingerprint tells me all the decisions that were made at every stage of the algorithm. Like, I suppose they end up with the same fingerprint. Run the algorithm, right? If suppose that there's some step where, so if both, run the algorithm in parallel on both independent sets. If there's any stage where a different decision is made, like if the choice of VI is different in the two cases or something, or no. Well, if it hasn't been different so far, then it won't be different. So essentially, like if there's ever a different decision made, what's going to happen is some vertex gets put in the fingerprint of one of the sets, but not the other. And that'll cause their fingerprints to be different. So like, for example, suppose you run the algorithm in parallel on both independent sets. So far, all of the things, every step was the same. And now let's say we get to some step where in S, like VI is not in S, but VI is in T. But then VI is going to go into the fingerprint for T, and it's going to get deleted from here, and it's never going to go in the fingerprint of S. So yeah, if one of these cases holds, then for one of the sets, it must hold for the other. And then if that case holds, then the processing that happens is going to be exactly the same, right? So if case A or case B, if the same thing happens for both of the two independent sets, all the decisions will be the same, and they'll end up with the same fingerprint, but they'll also end up with the same container, because all the things that were done to the containers is the same too. So yeah, if you end up with the same fingerprint, you must end up with the same container. Okay. Because literally that means every step of the algorithm made the same decisions. Okay. Questions about that? That's a bit, but that's the key kind of observation here. Okay. So now what we're going to do is do a really kind of dirty bound that's going to work. So here's the thing. What I can do is now say, go through all the possible fingerprints. What is a possible fingerprint? I'm just saying a set of size less than n over m. Go over all those sets, count the independent sets with that fingerprint, which, all of those independent sets with that fingerprint have the same container. So I can just say count subsets of the container. And somehow this is gonna work out nicely. So, well, nicely is a bit maybe an overstatement. This is going to be really ugly calculations that are going to work. So first, just to kind of formalize this, so let's define a function from, so when I write this less than or equal to, I mean, this is like we're doing like, a set choose k or something, but I'm just saying sets of size at most n over m. So take a mapping like this. Where if f is equal to fs for some independent set, then we define g of fs to be the container of that independent set. Okay. So I'm just saying for each fingerprint, like g of this thing, it doesn't really matter. I just say, what is your associated container? And that's a well-defined function, because if two different independent sets had the same container, the same fingerprint, then they have the same container.
What's F here?
So if, it's some element of this thing. So it's a small set, or So if, if f is any set that can be represented as the fingerprint of something, then I define g of fs to be this. And then if it's not, then just make g of f arbitrary. So I guess I'm saying for each element of the domain, if it is a fingerprint of something, then set g of f to be, or maybe I'll just write g of f here, g of f to be the associated container. If it's not the fingerprint of anything, like for example, if it has edges in it, just pick anything. It doesn't matter. So just, pick anything in the codomain and send it there. Okay. Seems extremely lazy and sloppy, and it's kind of amazing that it works. Okay, this is gonna get a bit messy. I'm not sure if we have time for it, but okay, so for each, for anything in this domain, let I of f be the set of all independent sets which have f as its fingerprint. Okay. And so, of course, the total number of independent sets is going to be, well, in fact, it's equal to the sum over all f, so in this set, of the size of IF. Right? Because every independent set has some fingerprint. And so if I sum over all the possible f, meaning all of the f in this set, take how many independent sets have that fingerprint, that's going to be, that's going to count every independent set once. Okay. Okay. Well, okay, let's do this. Sum from k is 0 up to n over m. Sum over all the sets of size k. And now I want to give a really crude bound on the number of independent sets that have f as its fingerprint. So by this observation, basically to pick a set S that has a certain fingerprint, it's the same as just choosing like a subset of like the container minus that or something, right? So it's, I guess maybe I'll just write this down and see, or, no, what am I doing? Just quickly look. Okay. Okay. No, sorry, minus k. So if I've got an independent set, it has to have size at most n over 2. So if I take the elements of f, and then I can add at most n over 2 minus k additional elements. Okay. It's a j. It wasn't a j, but it should have been a j. Okay, like this is counting independent sets of size, I guess j plus k. Anyways, I'm just saying you should pick j, like you could pick a certain number of elements of, this is the size of, this is the size of the container basically. Anyways, if you use a bunch of, throw away a bunch of stuff and use kind of basic, so maybe I won't, I don't have time to go into more detail, but if you throw away a lot of stuff, let m be large, let d be large, you will eventually get something like this. The important thing here is that like the number of containers is very small because the size of the container is small. So like, the important thing is that this is at most which you can say is, quite small if compared to 2 to the n. So let's say, that's a lot less than 2 to the epsilon n or something. But yeah,